Hello and welcome to Lecture 18. So it's been a while. If you remember, we had a holiday. We spent two class meetings talking about project proposals and meeting with groups, and that was really interesting. I'm really excited to see those projects turn out. We had a great guest lecture on Monday from Kevin talking about formification in Chisel. So remember way back to almost 2 weeks ago when we were last talking in proper lecture in this course, I was talking about changing gears from purely code concerns, thinking about how the physical design stuff crops up when we're actually writing this kind of code. In particular, we're talking about delay today, which is a very important, of course. It's also a well-timed lecture because our next guest lecture, which actually be this coming Friday, will be Sungwei from the University of Wisconsin, who will be talking to us about OpenTimer, which is a really great open source timing tool his research group makes, as well as TaskFlow, which is the parallelism library that's used to implement that tool. And so this is kind of your primer on timing to get prepared for the heavy-duty timing lecture coming up on Friday. Okay, so what are we going to talk about? We're going to talk about delay in your design, like where does it come from, and what we can do about it, right? And that's the thing. There's a lot of times I'm going to encourage you to use tools. That's the theme of this course, make tools do the work. There's some times when tools can't do it and need some help, and that's where we need to get involved. Okay, so we can go ahead and prop a notebook. Unfortunately, code's a little bit away, but we're getting ready now. Okay, so if you think about what caused delay in a digital circuit, when a signal changes, perhaps on the left over here, it takes some time before that change is observable on the right. And there's various forms of delay, right? It takes logic gates some amount of time to compute the next value. Also takes some amount of time for the new value to propagate through the wires. Additionally, if the wires in just a point-to-point link, but actually, connecting multiple outputs, the additional outputs can increase how long it takes that output to change, right? So I said I wasn't going to do it, but I lied. I guess I have to talk about it a little bit. If you want to use a meta analogy for electricity as water, right, you can think of, these cases possible passing only so much water through at a time. And so why are we talking about water? Well, think about signals on the wire, right? High voltage for 1, low voltage for 0 in binary. It's something similar for water, right? High water level in the water tank is a 1 value, a low water value, a low amount of water in a tank is a 0. And so these tanks are capacitors, right? They're basically holding some amount of charge in electricity or water in the water analogy. And so it takes time for that water to flow. And if we have more inputs to connect to, because of fan out, that's going to be more tanks to fill. So it's take more time for the water to get to the same water line, so to speak, right? And so, so in your design, at this individual, very low gate level, as designers, we often aren't looking at this because we're writing high-level statements, things like adds or muxes, and then trusting the tools do all the logic optimization for us, and we should do that. But we're talking about today to be aware of where these delays come from, right? Like I said, so there comes delay from within the gates, the wires, and also the fan out could also increase the wire delay, right? Even the gates themselves, the delay depends on technology you're using, right? So for example, in an ASIC process, usually you hope your gates are only 2 or 3 inputs. Too many inputs makes it a lot slower. However, an FPGA, which has LUTs, maybe 5 or 6 bits, you actually pay no latency penalty until you go beyond 5 or 6 inputs. It's actually, you're encouraged to use larger gates. So you can see already that landing complexities of which logic gates to use, that should be done by synthesis tools and the CAD tools. They know what technology you're targeting, and that kind of stuff. With regards to which of these is the bigger source of delay between gates versus wires, once again, it's also very technology dependent. Building an ASIC, perhaps if you have really good placement and really good design, the wire delay might be pretty small. It's largely the gate delay. Not really small, but maybe like a third or something. Versus on FPGA, the wire delay can easily be the vast majority, right? You often spend a lot of time on routing FPGAs. So it really depends. But the point is that either way, you're getting delay somewhere. Either coming from the gates or the wires. Questions so far? Yes? So the question is why might the delays be worse than FPGAs? Good question. So the wire delays are worse than FPGAs for a few reasons. Number one, as you said, was the routing, where because the routes are reconfigurable when you put on different bit streams, that's flexibility causes some circuit conditions, right? So there's some stuff there. Additionally, also remember that FPGAs are, unless you're using the hard blocks, going to be less dense, right? So your things you're connecting are farther apart from each other. So it has to travel physically farther. And rather than being, a perfect, custom wire for that one connection, it's actually, a route through a switchable network, right? The network is statically switched in advance by the bit configuration, but yeah, that flexibility adds some latency as well as the far distance adds some latency. So it kind of gets you both ways. Cool. Other questions? Okay, so then how do we talk about delay? Obviously, normally you might think about things like time. So for example, nanoseconds, which is, a billionth of a second. That's really freaking fast, right? That's so much beyond human comprehension, right? Seconds, sure, we can appreciate fractions of seconds as humans. If he's looking at like 60 FPS video, right? Um, that's, like 15 nanoseconds per frame or something. Yeah, you can kind of maybe almost tell that, but like, oh, sorry, 15 milliseconds per frame. What am I kidding? Yeah, no one corrected me. I'm sorry, 15 milliseconds per frame. But saying even 1 millisecond is already beyond the point you can comprehend. This is, a million times smaller than that, right? So nanosecond is already really small. But guess what? We have circuits that run in the gigahertz range. So how's that possible? Well, it turns out that some of the delays are, sub nanosecond, right? So that means we're in the picosecond regime, right? And guess what? If you're using superconducting logic, you could even be in the femtosecond regime. So they're going even super, super fast, right? That's the whole point of that stuff. But anyways, independent of these units, those are some raw numbers. It turns out as an architect and designer, we also talk about this in terms of a different unit, which is called fan out of 4 or FO4. And the reason why we do that is because of, technology rapidly changes, right? So someone uses one technology process, say 32 nanometer, someone else uses 14 nanometer some number of years later, they're going to get a lot of benefit from the fact these are smaller, faster transistors, right? And so how do you kind of make that more agnostic? This FO4 metric is basically saying just how many logic levels is your design critical path. And so as a result, you can now have this number to appreciate just how aggressively optimized your design is, right? So that way it is somewhat possible to compare design, let's say, from 10 years ago to now. Obviously, the frequencies are going to be different. Maybe not as much now with the frequency plateau, let's say 20 years ago. But the question is, how small is FO4, right? How am I in this agnostic point? So what does FO4 stand mean? Fan out of 4 referring to inverters, right? So how long does it take one inverter to drive 4 inverters? So of course, this fan out, there's going to be more capacitance here. So let's do some work. So how long does that transition take? For example, one technology many years ago, someone found this to be 18 picoseconds for a fan out of 4. Obviously, a real processor does more things than just inverting signals with trees of inverters, but it gives you a sense of, okay, this heavily optimized processor, Intel Pentium 4, with a really high clock rate at the time, 16 FO4. If you're talking about modern designs and what's possible, if your FO4 is sub 20, that's an optimized design. That's a pretty heavily pipeline design. You don't get there just showing up, right? You've put some work in. I believe the lowest that's ever been done in a real commercial product is around 14 FO4. That's kind of the roughly, I wouldn't say the limit, but the farthest anyone's pushed that. Understand that when you're at 14 FO4, the you have some timing constraints from your registers, right? Things like your setup time and your hold time and that kind of stuff. Those already are several FO4. So if you're running at 14 FO4, depending on technology, maybe burning 4 or 5 FO4 on just the registers. So that means your logic is really shallow, right? You really have pipelined the hell out of your design at that point. But like I said, for us, it's kind of you need to talk about things. Okay, we talk about, how many FO4 is this design? And, you kind of appreciate that. Once again, you're probably also good to be skeptical is, wait a minute, FO4 supposes your design's been synthesized and, an actual logic has been chosen. Yes, it's not something you can just look at chisel and tell right away, but these are just units to be aware. Cool. Questions? Okay, so now that we have appreciation for what the units for delay is, of course, we also care about things like the critical path, right? Which is the longest delay path, not necessarily the longest in dimensions, but longest in delay for anything to change, right? And so, and technically, we define this as under the worst case conditions. It turns out a lot of times the latencies of certain transitions actually depend on the input values, right? So it's not the same to go from 0 to 1 and 1 to 0 depending on the logic gate, right? Those are going to be different. So you can imagine when you have a whole network of gates, depending on the exact adversarial combination of the zeros and ones here originally, and then the zeros and ones the next cycle, that's going to change the latency to get through here, right? And so the reason why we care about the longest latency path, well, we have a synchronous circuit with a clock, right? We want to make sure that the clock period is greater in time than the critical path delay. In other words, um, the circuit works. If we have a clock period less than the critical path delay, if there's ever a situation where that critical path is exercised, we're going to get the wrong answer, right? Now, people may be asking about things like, oh, what about overclockers, right? Well, overclockers are, reducing the clock period by increasing the clock frequency. And yeah, they're seeing how close they get to that critical path. And it may turn out that the vendor of their hardware had a lot of margin there, so they can overclock and it works just fine. It may turn out that they overclock too much and it stops working. Or it may be in between state where technically you're not meeting critical path latency anymore, but critical path happens really rarely. Or if the critical path is violated, it doesn't cause the computer to instantly crash. And so in case you can live along for a little while. So it depends. But for the most part, as hardware designers, we're very focused on this critical path because it sets a constraint on the clock frequency, right? Depending on how much, margin you put beyond critical path for frequency, sure, but this still sets the clock frequency, right? And so if you can reduce the critical path, what happens? Well, you can increase clock frequency, go faster, or actually you can turn down the voltage. If you turn down the voltage, the circuit goes slower, but takes less power, right? So if you have a certain performance constraint and you have the clock frequency to meet that, but actually if you can shorten the critical path, keep the same clock frequency, turn down the voltage, save power, right? So you really want to optimize the critical path. What's interesting is that in terms of delay, you actually don't care too much about paths that are less delayed in a short critical path, or shorter, so to speak, right? Because they don't impact the frequency. And so what's interesting about that is modern CAD tools are pretty good about this. They don't just have, one AND gate to pull from, right? They often have multiple variants to choose from, or multiple conditions, multiple voltages, special voltages, that kind of stuff. And so they will pick to use the fastest gates they can along the critical path, but along the things non-critical path, they can often get by a much slower gates. They can also perhaps, when they do placement and routing, they can give these things longer routes because it's not as important. They can use that slack to really try to improve critical path, right? So you really want to take advantage of making a critical path as short as possible, and then things not a critical path, they aren't critical. So sometimes you can often save resources there to make it up for it. Cool. Questions? Okay, so then how might we go about this designing? So as part of your large tool flow, whether it be an ASIC or FPGA or something, you're going to have your, design synthesized, perhaps even placed and routed. At some point, you want to convince yourself, how fast can the circuit run, right? And so one way of doing that is something called static timing analysis, or STA. And it's the process of trying to analyze your design and figure out, various timing properties of it. So there's a number of things you can check with STA. But for the sake of today, we're going to be asking ourselves, what is the critical path latency, right? What is the longest critical path? Now, you can imagine many such algorithms are doing this. Today we're going to show a really simple forward and back algorithm where in the green, we have the delay of either a gate, let's say in this case 4 time units, or a wire, let's say it's 1 here or 5 to go across here. And so you see, the question is, well, how long does it get through the circuit in the worst case? Well, you can kind of see the algorithm right here. Okay, let's say we start with all the orange numbers, right? So, originally all the inputs come to circuit at the same time. Say it's a new clock cycle. They all take, the initial wire delay. So, 1 cycle here now it means it arrives at this, gate 1 time cycle later, 1 time unit later. In this case, 3 time units later. Okay, so then when is the output of this change? Well, the inputs changed, last changed to 1, so the output's going to change to 1 plus the max of the inputs. So, okay, 5 time units now it's changed, 3 down here, etc. So you kind of see we propagate through this, right? We kind of have this forward pass, we're propagating these times through. In this case, let's see, for example, we have 2 inputs arriving at different times. Assuming the worst case, we're going to take the latest of the inputs, right? This one arrives later because it takes this longer path going through this gate and this long wire, versus this other one just came through a long wire to start with. So then we're going to start from here. Okay, it takes 10 time units to get here, and then 2 time units to get through this gate. You see, eventually we get to the other end where, yes, we get the final answer after 23 time units, right? So we know, first of all, that this circuit, it takes 20 time units to get through it based on this simple model. And I should clarify that this is a very simple model, right? A lot of times, these logic gates, their time behavior is far more complicated than simply saying, oh, it takes only 2 time units, right? You can imagine, like I said, depending on the input conditions, certain transitions take different times. So it comes 0 to 1, 1 to 0 takes different amount of times. Additionally, if we want to, make this realistic for real process, because you configure things like what kind of margins you have in there for process variation or for temperature and that kind of stuff. And you put some, some margin in there. It kind of all comes together, right? But the result is, yeah, we have this time over here. And we also, of course, as a designer, we're very curious about knowing what the critical path is so we can go ahead about fixing it. So you can trace backwards, picking the largest arrival at each step of the way to kind of see what's the critical path. Oops. And if you do that, we can kind of see this right here going backwards, right? We say, oh yeah, this one, so this is the latest. Okay, this is the latest input. This is the latest input. So we see, oh yeah, going back to the prior slide, the one I showed in the prior slide does show the critical path, right? So in this case, you see the critical path actually in this case branches out. That's not uncommon. It's not just a single line. It can sometimes branch out. It can actually merge back in sometimes. It can branch and fan. But like I said, the critical path is what we care about. And static timing, also STA, is one way we can go about analyzing this. And so Open Timer can do this with a much more sophisticated algorithm. We'll see that lecture about that on Friday. Cool. Yes? It may be done at the transistor level, depending on the tool, yeah. Oh, good question. So depending on what implementation technology might my critical path change for a given design? Absolutely. So some designs have a really, flawed critical path. That's really obvious. Okay, that might not change. But most designs, if you're doing it right, uh, you don't have just one critical path. You have a few things close to critical paths. And so depending on technology constraints, that can change. So for example, a common constraint for academic test chips uh, is you often, especially with modern technologies, you can make pretty efficient logic in pipelining, but then you get bottlenecked by your SRAM because, it turns out SRAM, if you just take vanilla SRAM, it may not be that fast. It may not be running at, 2 gigahertz, whatever you want to run it at, right? And so that becomes a critical path, right? Meanwhile, on FPGA, sometimes the VRAMs are pretty quick, right? And so maybe that's not your critical path. Maybe the critical path is actually a logic path that goes through routing or something. Yeah. So when I say ASIC, I'm using that umbrella term to cover both custom chips and CPU chips. It just means to me something where you fabricated silicon rather than an FPGA. But in terms of clock frequencies, yeah, I mean, we know CPUs can often get, 4, sometimes even 5 gigahertz. I believe some of them even now, some can clock to 6 in turbo. Um, Non-CPU chips sometimes are lower frequencies, perhaps 1 or 2 gigahertz, right? I believe GPUs are like 1.4 or something like that, depending on the model or something. Someone here can correct me. 2.5 gigahertz for GPU? Like an NVIDIA one? I think they're lower than that. You can double check that maybe. Um, yeah, so AMD may run faster, but saying NVIDIA ones I'm aware of, I think they're between 1 and 2. I'm not positive, but that's my guess. Yes. Oh, great point. So here I'm talking about critical path in terms of the longest path. Isn't there a situation where sequential circuits can fail if something changes too fast? Absolutely. You must forgive me for not knowing a name for that. But yes, these usually referred to as as like a hold violation. Yeah, so if you have a hold time violation, that is definitely a problem. And that is definitely something you want your STA tool to warn you about. So like I said, the STA tool is not just going to check critical paths and check multiple things. And one of the things you want to check for is, what are your likelihood or probability of having various timing violations. The critical path, technically, the time is, a setup time violation, right? Because if you have the frequency too fast, you're not going to have the signal stable enough before the setup time. But you can imagine, as you said, if you have a path that's too fast, you can have a hold time violation, which is a whole other kind of issue. Um, Usually those kind of things can be fixed by tools, hopefully, the whole time ones. You have an answer? Oh, wow. Okay, so much faster. It's 49 years NVIDIA? Oh, wow. Way higher frequency than expected. Okay, well, there you go. Here we are in 2024, living in the future. GPUs run 2 gigahertz range. Yeah, and like I said, sometimes your phones can break 3, right? So like I said, gigahertz is, the standard. Yeah. Unfortunately, date myself. When I was a kid, we were so excited to get to 100 megahertz and then multiple hundreds of megahertz. And oh my gosh, gigahertz is so fast. And now it's been standard for a long time. Yes. So the STA tool is going to just tell you what's happening. It's then going to instruct the CAD tool you have a problem. The CAD tool is hopefully going to fix it for you by, as you said, for a whole time violation, adding some sort of delay element in there. Yeah. Can you have multiple critical paths? Absolutely. So maybe it's good to go to the next slide. Then I can answer your question. So, like I said, we're really at a critical path for frequency reasons. Um, and part of the reason why is the tools can only do so much optimizing critical path, and sometimes we need as humans to intervene to fix it. Some of the things we talk about, like hold time dilation, sometimes the tools can fix that on their own. But um, here's the thing, right? When you want to fix these critical paths, turns out most paths are short, right? So this is the distribution of how many paths there are in design versus the delay. Most of the delays are pretty short, way less than target clock period. However, when you first start trying to optimize your design, even if you have some sort of target period in mind, you're going to have multiple paths to break it, right? So what are you going to do? Well, you're going to take the longest path, trace it out, figure out what it is, and then try to change your design to remove it. So actually, it's an extremely, extremely time-consuming process, right? So if you want to make an ASIC design that runs at 1 gigahertz, you can probably just write pretty reasonable RTL, ship it, you're done. You want to run at 2 or 3 or 4 gigahertz, takes some significant engineering effort. A lot of it goes into this kind of critical path optimization, really kind of balancing your stuff out. Unfortunately, fixing critical paths is actually really annoying, like I said, because by the time you see the timing report, the names don't make sense, right? Because your design's already been synthesized. So what you thought was, your Verilog or chisel statements have now turned into a lot of nets and gates, and you got to try and parse that backwards to your design. There are some commercial tools that help with attribution. Unfortunately, the open source tools do that. But the attribution is a kind of a common problem of, okay, I knowing exactly which lines to touch to fix a certain critical path is not always obvious. It takes a little bit of thinking and reading, and yeah. But however you do it, you kind of have this process of find the longest path, figure out what it is, look at your design, change your design to reduce the delay of that path. Great. So you can probably solve a lot of these really bad paths with some effort. You may need to even change your architecture. But at some point, what's going to happen is, guess what? You keep fixing all these paths, and you're all going to get them just under the critical path. Because right now, once it is a critical path, okay, make it go faster. As long as your critical path, so you forget about it. But then guess what? If you fix all the other delays, that path will be a problem again. So like I said, after you fix your critical paths, you may have a time distribution that looks like this. You have a lot of paths that are really close to the critical path delay, which if you're a manager in a hardware design project, this is a sign you should talk to your upper management about, settling on this target period, because to go faster, it's going to be a lot of human effort to push these paths over, because there's a lot of paths there. At this point, there's only a few paths, right? But now you've already fixed the easy ones, and they've all kind of piled up near the critical the target period. To go faster is taking a lot more effort. So like I said, this is unfortunately time consuming. This is why you often have big design teams. In this course, we've kind of focused on the joy of hardware design, and the joy is, I'm gonna go code up some interesting hardware and do some generation, and that works just great. We do the front end stuff, but if you're doing the back end stuff, really trying to optimize the period, this is where your time goes. Also, verification, of course. Okay, so as I said, let's say you determine there's a critical path as a problem. How do you go about doing this? Normally, if you're looking at the critical path as a problem, the tools have already tried optimizing it, right? So my attitude is usually the tools do the work. You shouldn't be doing things tools can do. That's time wasted by you, right? So you want to make your effort complementary to do things that tools can't do. If you're doing things tools can do, that's redundant, right? And as we're all learning right now, LLMs are able to do more and more. And so we will, over the next few years, keep passing off more of what we do to some sort of, advanced automation, right? So keep being paired with what tools can do. And if the tool can do what you can do, great, let it do it and you can do something else, right? Doesn't mean you can do nothing, you just do something else. What do tools do? Well, they're actually, even before this AI era, extremely good at logic optimization, right? There's been decades and decades of, I have these logic functions. How do I, share gates, reduce gate depth, choose minimal gates? It can do that stuff, right? And let's say these tools are smart enough where it'll run through, recognize the critical path, and then you actually go back along the critical path and see, what, can I tweak things around here to make this faster? Maybe I'll change the placement of routing and try and shorten the path. Maybe use faster gates or change the logic structure to reduce the gate depth. It can do that kind of stuff, right? It can also do stuff to, burn more power to try and really save the critical path. Okay, I'm gonna use these bigger, faster gates, burn power in critical path, hopefully save design in the long term. The point is, all these changes do not change the semantics of the design, right? They're able to kind of use logic transformations, but it's still logically equivalent, right? You still should pass the logical equivalence check, on LEC. And like I said, by the time you look at critical path as a designer, the tool's already tried to do this, right? So it's already done this in many cases successfully, and perhaps you take it for granted and realize it's already done this. But there are times where after a tool is done what it can do, there's still a critical path, its latency is longer than you would like. And the only way to improve it involves actually changing the semantics. That is the functional behavior of that piece of code to make the tools able to fix it, right? So yeah, you are going to need to change it. Now, sometimes it's as simple as, figuring out a way to insert a register along the line, along critical path. But other times you got to do a much more major, much more fundamental architectural change. And once you make those changes, then you can let the tools run again. So you can see this process of, run the tools, get results, understand the results, think about the design, change the design, let the tools run again. Hopefully the delays are reducing, right? You start to see where time goes, right? Cool. Questions? Okay, so like I said, one common trick is pipelining, right? So if you have a critical path, we only care about getting from one register to the next register. To go beyond multiple registers, let's do multiple clock cycles, right? So within the clock cycle, the critical path is from the output register, the longest latency path to the next register and across the entire design. So perhaps there's some, really obtuse situation in your design. We have this long combinational, huge gate depth over here. Well, what do? You can put a register in there, break it up, and then you have a shorter combinational path. Thus, you can reduce the critical path latency. Now, it's important to remember what we've done. The absolute time, nanoseconds per seconds to get from here to here takes, X picoseconds. To get from here to here now will take at least X picoseconds, perhaps even longer, right? Because of certain delays added by the pipelining. However, the clock frequency is improved, right? So that way we're okay. Now, to be able to do this, right, you need to have a design that has parallelism, right? At this point, we have one unit outstanding. To do this, we need to have 2 units outstanding to get this benefit. If I don't have 2 units outstanding, I do unit 1 part A, unit 1 part B, unit 2 part A, unit 2 part B. That's not going to be any better, right? You'll have twice the frequency, but half the throughput, right? So it's going to be the same overall throughput. So the good news is for a lot of arbitrary designs, it actually is pretty easy to pipeline. Now, many of you have taken pre-architecture with me, and you've seen me talk about pipelining in CPUs. CPUs are a special case where we spend a lot of time thinking about the design, but also the nature of ISAs is that they're quite sequential, right? We have, a sequential stream of instructions, and so the result, there's actually a lot of dependence between instructions. We spent so much time in that class talking about how to identify when instructions are parallel and independent, right? But in general hardware design, often you have that parallelism, so it's actually not too hard to just toss some registers in there to get that parallelism to get things going, right? Now, ideally, we'll put it someplace where it's, you can split the delay up. Sometimes it's very clear semantically where it should go. However, as a human designer, choosing to move logic from this side of the register to the other side of the register, or vice versa, that can be very time consuming. So we're going to fix that with something called retiming on the next slide. But before we go to, I'm going to pause for questions here first. Let's fix that. So, okay, how do we move logic across registers? Once again, let tools do the work, right? So this actually was proposed decades ago by Charles Iserson. In that year's ACM Doctoral Dissertation Award winner was this idea of register retiming. So it's actually been available in many CAD tools ever since. So what does it do? Well, guess what? If you have the registers, you can let the CAD tools figure out how to move registers around the design. So it's not so much inserting registers. The registers already exist, but the tools get to decide where it goes. So it can move some logic gates across registers across logic gates, however you want to think of it. Sometimes some retimers go backwards as they take registers at the end of design and pull them towards the front of design. Some retimers are forward retimers. You put registers in the front of design that pushes it into design. But either way, the tools are doing this. Now, in terms of how this is allowed, it depends, right? From the input point of view and the output point of view, the semantics are unchanged, right? Data goes in, it comes out X cycles later, that's unchanged. So in that point of view, the semantics are not changed. However, the content of the registers in between is now different, right? So if someone's expecting certain values in registers, because you have logic on both sides of them, you have to kind of be prepared for that. So that's where the devil in details is. The retiming is how do you move registers through logic networks to make sure people depend on the values of the intermediate registers to get the right results, right? it can be done. Um, and so, as a design methodology, for example, in Chisel, we would love to just chuck down some registers at the end and let the tools retime through the design. This works quite well with a lot of commercial grade ASIC CAD tools. Unfortunately, some of the tools, especially I'm going to name names, Xilinx Vivado, uh, does not do a great job with this, right? So you use a different methodology. But in the ideal dream case, that's the way it should work. Um, One of the other challenges of retiming is now that you change the semantics of the internal registers, even if your design has the correct result, it may complicate your verification team's efforts because if they now want to verify your design or do logical equivalence checks, it's a little bit complicated. Once again, the expensive, pricey commercial tools have solutions for this. But for us, for those living in the open source world, we can only dream about that right now. Cool. Other questions? Yes. Great question. So where does registers come from? So they need to be in the design. So the next slide I'll show you in Chisel how we're going to put them in programmatically. But yeah, retimers can't automatically insert registers. They need to already exist. And then retiming is just choosing where they go. Now, some of you, for example, may be familiar with something called HLS or high-level synthesis, right? High-level synthesis is a hardware methodology where you describe, as named, a higher level semantics, more of the functional high-level behavior, and let the tools do a lot of work. So one of the things the high-level synthesis tools will do is they will choose things like how much to pipeline things, how to block things, and that kind of stuff. And so in that case, in the spirit of making tools do the work, they are choosing pipeline depths at a high level. So humans aren't thinking about pipeline depths in that methodology. They're just thinking about function, but the tools think about pipeline depth. In the Chisel world, for us to think about pipeline depth is actually really easy. There's no data dependencies. We have perfectly parallel work. It's as simple as putting a FIFO in at the end of your design. So now a pipe is a object in Chisel standard library. It's a little bit different in the queues you spent so much time talking about. So the queues, remember, we had the coupled interfaces. They could do feedback, back pressure, that kind of stuff. The pipe is literally just a shift register, right? Cycles stuff comes in and registers, comes out and cycles later. There's no pausing or stopping. And that's really important because these are really simple registers with very, simple connectivity patterns. It makes it much easier for retimers to work in this. And like I said, this methodology actually works pretty well with ASIC commercial tools, right? So you can write your module, and it should be pipelined. Make that a parameter, put a FIFO at the end to have that parameter, and then there'll be registers at the end of your design, and just the ASIC CAD tools will pull them back through design and perfectly pipeline it. Unfortunately, Vivado is not great at this, much to my annoyance. Yes? Is there a way to optimally determine the registers by the tools? Yeah, so the reason why I'm pushing back on this question a little bit is I would say someone needs to determine the right number of pipeline stages. It doesn't necessarily need to be human, right? So there are some frameworks out there that are possible for language like Chisel. If you have a generator with a lot of parameters, this is a parameter. It doesn't mean parameters set by humans. You can have a automated tool flow, set the parameters, and explore multiple designs for you automatically, right? So that's called design exploration, right? We try multiple design variants. And that's what having generators is rather than having, here's my design, I hope it's good. You say, here's my combination of generators. Hey, design exploration tool, try out multiple parameters, see what looks good. And so through exploration, you may find, this particular module is good as 4 stages, the other module is good at 2 stages on a technology. And then a year later, for new technology, you run design exploration again, and you find, I should once again change those parameters. So this is kind of this interplay between humans and the tools. As Chisel designers, right, our goal is to make generators with parameters and let the tools do as much work as we can, right? And so, we'll expose this capability, right? If you try to make this particular module run at a certain frequency, the tools can only do so much. At some point, it's going to need you to give it more registers so it has more ability to, retime and balance the stages. And we can choose that depth with a parameter, for example. So this is a really simple methodology. It's just to simply put on a few cycles. Unfortunately, it doesn't work well in FPGA. And so methodology I'm using a research group, which still makes me cringe, is to analyze your Chisel about all places the register might need to go, Doesn't mean it's going to be the final resting place. The FPGA tool still can do some retiming. It's just very local what they can do. So basically, we have code that every place the register might be able to go, we have some sort of annotation. And then there's still a parameter, once again, trying to maintain the complexity reduction. So yeah, I want to have, only 4 registers in this design. Let's say that particular annotation occurs 8 times in the design. So somehow you need to prioritize which of those annotations get the register, which of those ones do not get annotation, or just pass through. That's a current methodology. It's doable in Chisel. Doing that in Verilog would be painful, but it's also doable. I often ask, other researchers or other practitioners in the industry how they're handling this. And yeah, people have told me they use all sorts of, pragmas or other tricks in Verilog to have registers they can kind of turn on or off to make certain frequencies in FPGAs. We can do that kind of stuff a little bit cleaner in Chisel, but it's still, in my opinion, more human intervention than I think is necessary. Cool. Yes. You, because you run a tool flow of all 3 modules together. Yeah. So the question was, okay, if multiple modules feeding to each other, how do you, make sure you're working in one critical path that has the, and my answer is you do all the modules together, right? You run your entire design because yeah, a lot of times the optimizations and placement and that kind of stuff is a global problem. So if you do things in isolation, you can get numbers. Those tend to be the best numbers that are possible. And once you have, your module, not just in isolation, which now can use all the space it wants, but, once it's compacted multiple sides by other designs and competing for routing resources, that's going to be a more realistic number. So you don't want to run the whole design. Unfortunately, running the whole design takes a long time because it's a big design and slow tools. Or at least, maybe not the whole design, but your whole block, or you want to call it, right? Whatever that thing, yeah, yeah. So that was one opportunity. It's, okay, you know what? If you can just simply put some more registers in your design, let the tools do some retiming, or maybe put registers closer than need to be. Another technique is to actually look at the logic and to recognize sometimes your logic can be made more shallow. And so, like I said, the CAD tools that are hands tied behind their back, in the sense that they cannot change the functional behavior, right? If you say I want A and B from in Verilog, right? The tools can't give you A or B. It's not okay, right? So that they're constrained by that. And so it may turn out, not intentional, but guess what? If you have a giant design, modern chips, tens of billions of transistors, guess what? It's going to be, there's some situation where somehow there's a corner case, we have this complicated logic path, and the tools do not know how to optimize this, or they actually can't without changing the semantics. So what happens? Well, this may be one of those times use a human ego in there and change the logic structure, which is rare, but like I said, in large designs this will occur. So what can happen? Well, if you have a long path, you can put pipelines in there. We talked about that. But sometimes you have things where the logic depth just grows linearly, right? Remember we saw a few weeks ago when we designed our priority encoders, our priority encoder design grew with the number of elements. If you want to do like 1,000 element priority encoder, that's going to be really hard to do in one cycle of the technology we were using, right? Sometimes instead of having a linear depth thing, you can make it a logarithmic depth thing by using a tree. So we'll see an example of that in a second. And so my advice for this is, yeah, it's kind of fun to go optimize this stuff, but like always, whenever you're optimizing, before you roll up the sleeves and actually do it, you should make sure it actually is the problem, right? So first, you confirm this thing is on the critical path. If it's not on the critical path, you don't care about it. Don't worry about it. And so you only get matters if it's on the critical path. And instead, if it's on the critical path and you know it's because the logic stuff is too deep and you think there's a chance you can reduce it rather than pipelining it, then sure, then you can try this other stuff. So how about an example? Well, here's a reduction. So if I want to, add up n numbers, I'm going to need n minus 1 adders, right? And if I have these 2 input adders, okay, add 2 numbers, add 2 numbers, add 2 numbers, add 2 numbers. Now, guess what? What's the logic depth? Well, it's going to be n minus 1 adders, right? Now, if I did this in the tree fashion, log n depth, right? So it's actually substantially shallower sometimes, right? So for example, let's say I had 16 numbers, right? We're talking 15 deep here versus 4 over here, right? That's a huge difference, right? So Why can't the tools do this? Well, if you're using additions such that overflow is possible, these are not mathematically the same, right? Because the overflow happening here is different overflow happening here and then propagating over down here. Um, these are not quite exactly the same. However, you as an application designer or hardware designer, you may notice it's okay. And so you may be okay with this particular addition order. But guess what? If your code's expressed with this addition order, the tools can't fix it, right? They have to do it with your help. Yes. Good question. Sort of, but it's not going to give you quite what you think. So in Chisel, the question was, there is an ability to have, the growing additions. That way, there's no chance of overflow. So we can kind of work this out ourselves, right? So let's say originally these are k bits for simplicity. I would say n, but we already have n already used. So these are k bits. Okay, so you add two k-bit numbers that have no chance of overflow. You're going to have this be a k plus 1 bit result. So k plus 1 bit thing plus a k thing, to be absolutely pessimistically, safe, conservative safe, you need k plus 2 bits, right? So in other words, after this, you need k plus n minus 1 bits in your adder. If you're doing the tree addition, okay, k bits plus k bits, k plus 1. K plus 1 plus k plus 1, k plus 2. This is log n deep. So actually the resulting width here is going to be different, right? This is actually going to be k plus log n bits, as opposed to k plus n minus 1. So this is why it's important to understand the semantics of the numbers you're adding. And there's only situations where subtle things from the point of view of a human may have, profound constraints for tools we don't intend. I see confused face. I'm going to take a follow-up question. Well, this one, so you're going to add 1 bit per adder. No, so it says you're going to add 1 bit per adder, right? So it's going to be k plus n minus 1. There's n minus 1 depths of adders, and each adder adds 1 bit to the output. This one is going to add 1 bit per adder, but it's only log n depth. So it's going to be k plus log n versus, so the difference is, n minus 1 versus log n bits in the final result. If you're being extra conservative. Yeah, okay, so that's a great counterpoint, and I'll try and best convey this for the recording, and I can definitely explain this. I'm happy to have this conversation. So, um, first off, the point was correct about mathematically how many bits do we need to actually not lose anything to overflow. The answer is yes. K plus log n is sufficient. So the tree with the growing adders will not lose data. That's sufficient. So the fact that this other one over here is doing not just k plus log n, but k plus n minus 1, that's overkill, right? So what's going on with that? Well, digging deeper, right? The semantics of chisel and fertile is such that if you have the non-truncating addition, you take the max of the 2 input widths and you add 1 to it. So that particular methodology is going to result in the over-provisioning of bits here. It's overkill, right? And the reason why is if you're, as you go down this tree, or not this tree, sorry, this linear combination, even though you may have some result, let's say it's, k plus, n2 bits, whatever that is, you may not really be using all those k plus n over 2 bits, right? You may not really using all of them. You're only using maybe some of them. The tools don't know that, right? And so it's going to, once again, add another bit for the adder and to keep growing it. So because of the language semantics and because chisel and fertile specify, what is the width of a non-truncating addition? Well, it's the maximum input width plus 1. Because of that constraint, this design is going to have or provision bits. I'm going to agree with your point that it would be nice if tools could do this. I do not believe they'll currently do it on their own, right? No, no. Like I said, the language semantics make it impossible, right? If you use a non-truncating addition, it has to give you those bits, right? That's what semantics of the language says, right? Now, what you're saying is you want to specify the property that, hey, I just want to add 16 numbers together, don't lose anything, and there's a way to convey that into language. That would be nice. That's not currently in the language, right? Language, as we know, is you're going to have to build a module which does this addition, and you're going to use recursion, functional programming, a for loop, whatever, to actually do the additions, right? And so the point is you're going to call that, plus operator with the non-truncating symbol on it, however many times you call that. And once you've done that concretization, right, you've kind of locked it into a certain semantics. Now, like I said, from a philosophical point of view, yes. If you just say, hey, tools, I want to add 16 numbers, don't lose anything, but I don't care about the intermediate evaluation order, it could definitely solve this. But that's not, to my opinion or knowledge, currently possible at Chisel. Maybe Chisel 7, which is coming soon, will have that feature. I don't know. But yeah, great conversation. Yeah, like I said, these subtle things in languages you do that doesn't matter to you as a human, but it can really constrain the tools. And so you have to understand a little bit how tools work. And if you understand how tools work, you can better understand how to, get them unstuck. But yeah, I think it's another point. Yes. The reduce is also specified as an order. Uh, yeah, plain reduce is not guaranteed to do a tree. It will do it linearly. Yeah, so this is a question we covered in the functional programming lecture. So why have reduce versus reduce left versus right? So the reason why reduce exists, I use it as simplicity, but semantically it's there in the language because there are some collections which, if you don't have a notion of a linear sequence, there's no notion of left or right. There's just a collection of elements. Like imagine a set, right? What is left or right? Who knows, right? Only a seq, which is an index collection, you have like notion of like left and right or increasing, decreasing index. And so that's the reduction for when the order is unknowable. That happens to be mapped to reduce left on an order collection by seq. That's an arbitrary choice. But yeah, I think we're all on the same page where after the long conversation, we would agree for small n, linear is probably just fine. But for large n, we all know in complexity, linear versus logarithmic, linear is going to get you. So we want the tree. Well, how to get the tree? Well, let's try coding this up. So rather than doing a full-on reduction, let's just count bits, right? So in other words, we're given a module which takes in, n bits, and we just want to count how many of those bits are 1, right? So how can we do that? Well, we're going to see multiple implementations. So the linear pop count, we're using recursion. What do? Well, we simply just take the bits, and what do? Well, we go through them one by one. Now, the base case, of course, is when the collection is empty with nothing else to add. But when there is stuff there, sure, let's go ahead and, add the bit to the recursive call, right? And the recursive call takes, n minus 1 to things. You give me n bits, and I have n minus 1 bits. We keep going until we get down to 0. So we go ahead and, okay, we right now are using the linear pop count. So if we go ahead and now look at the Verilog for this, here's what we see, right? If we're doing a depth 4 thing, yeah, it's going to go ahead and have our 4 bits coming in. And yeah, we're going to keep adding them up. And because we're doing the non-truncating addition, you can see the width is actually growing. Where originally, we have just 1 bit and we will add 0 to it technically, or concatenate 0, but then you see it kind of grow. We keep having this capacity being added on. So the result we finally have is 5-bit signal because we, uh, had the steps. Now, that's linear. We knew this was going to happen. Let's see if we can't do better. Okay, well, what about tree, right? Well, to do a tree, it's a little bit more clever, right? We have to think about, okay, well, given a sequence, uh, obviously, if I have 0 elements, well, this is 0, so I don't have anything to contribute. There's nothing. There's no ones there. If I have 1 element, because we're basically just how many elements are given the size, right? I'll just give you that value right away. If I have more than 1 element, I'm going to split it in half. And so this is take and drop. So this is the first n over 2 things of the element versus of the collection. This is the last n over 2 things, right? So take and drop are complementary. Two of them combine is all of the elements. And so just using some nice chisel, some nice Scala here. Yeah, so 2 recursive calls, right? Give half to one collection, one half to the other thing, recursively call from there on. So we go ahead and try the tree pop count. Yeah, let's see how this maps out, right? And then, yeah, guess what? Like we hoped, right? We have the first layer, these two things. They're both 2 bits, right? And then the final result is now only going to be 3 bits, right? Because we're not having that extra bits we were just talking about. Cool. All right. And so then the natural question is, well, I always show things written manually in this course and say, you know what, by the way, this is in the standard library. Guess what? This is in the standard library. And so what does it do? Let's go ahead and see. Looks really similar. Yeah. My comments kind of gave me away because I took this from the chisel version. So yeah, guess what? Standard library, folks, they've already optimized some of this stuff, right? In this case, for pop count, it's already a tree-based reduction. It's already nice and efficient for us. As you can imagine, when possible, this is why it's nice to have reuse. Because when you have reuse, that means the person who made the thing that's being reused can justify more effort to make the thing more optimized, perhaps being tree-based or whatever it needs to be, whatever that complexity is. And then everybody will all get a benefit from it. So isn't reuse great? Cool. Any other questions? Oops, don't delete. So that's today's lecture on delay. So hopefully you got a flavor for this, right? Remember, delay in the real design comes from gates and wires. The tools do a lot, both to analyze and fix this. However, at times they get hung up, and that's where we can come in and help. The most common thing we're going to end up doing is instant registers helping with pipelining. And that's an architectural change. It needs to be done by humans for now. Hopefully, we'll have tools to automate that in the future someday. And then other times, like I just demonstrated right here, there's a logic depth issue. And sometimes this happens, very commonly it happens in priority encoders or things like that. And you got to kind of deal with it. Cool. Okay, well, that's all, folks. So remember, Friday we have a guest lecture. It's going to be via Zoom, but it'll be great about a leading edge timer, SDA tool, and the parallel library behind it. Sounds good. Okay, thank you.